Imagine if everything we experience, our sense of location, motion, the very flow of time, is not a fundamental feature of reality, but instead something that emerges from deeper, more abstract processes. What if space and time themselves are not the basic building blocks of the universe, but consequences of how information is stored, transmitted, and protected at the quantum level? This idea might sound more like philosophy than physics, but it's one that modern theoretical physicists are taking increasingly seriously. Among them is Sean Carroll, a theoretical physicist who has helped popularize and explore the mind-bending notion that the structure of space-time might actually be the result of quantum error correction, a concept from quantum computing that ensures information isn't lost in fragile quantum systems. To understand what this means, let's first unpack what quantum error correction is. In classical computing, we have techniques like parity checks to detect and fix errors in data transmission. But quantum information is even more delicate. A quantum bit, or qubit, can exist in superpositions of 0 and 1, and any interaction with the environment, called decoherence, can cause that quantum state to collapse, effectively destroying the information. To protect against this, physicists and computer scientists have developed quantum error correction codes, which spread quantum information across multiple entangled qubits, in such a way that even if some parts are damaged or lost, the overall information can still be recovered. Now here's the mind-bending leap. What if the universe itself does something similar, not just with information stored in a computer, but with the very fabric of space and time? This idea starts to make sense when we look at how space-time behaves. In certain theories of quantum gravity, like the ADS-CFT correspondence in string theory, this is a duality that connects a higher dimensional space-time with gravity, the bulk, to a lower dimensional quantum field theory, without gravity living on the boundary of that space. What's astonishing is that all the information about what's happening in the higher dimensional space can be encoded on the lower dimensional boundary, a bit like a hologram. This led physicists to ask, could the connection between the boundary and the bulk be doing something like quantum error correction? And the answer, surprisingly, is yes. In 2015, a team of researchers, including Daniel Harlow, Fernando Pastowski, John Preskill, and others, showed that certain toy models of ADS-CFT behave just like quantum error correcting codes. The way the bulk geometry is reconstructed from the boundary data exhibits all the features you'd expect from such a code: redundancy, protection against loss, and the ability to recover missing pieces. What this suggests is profound. The geometric structure of space-time in these models is not just a background where physics plays out. It's actually built from the underlying entanglement structure of quantum information. In a way, space is stitched together by entanglement. Remove the entanglement between parts of a system, and the smooth fabric of space begins to tear. Sean Carroll takes these ideas seriously and pushes them further. In his research and public talks, he argues that this isn't just a curiosity limited to exotic models of string theory. It might be a deep clue about the real nature of our universe. He proposes that space and time themselves might be emergent phenomena arising from the behavior of quantum information under the rules of quantum gravity. Think about that for a second. We're used to thinking of the universe as a stage. Space is where things happen, and time is when they happen. But Carroll and others suggest that these might not be primary ingredients. Instead, the true foundation could be quantum states evolving according to simple rules. When those rules are structured in the right way, say, in a way that naturally protects information from loss, they give rise to the appearance of a smooth, continuous space. and the familiar ticking of time. In this view, the flow of time doesn't exist out there in space-time. Rather, it emerges from the relationship between quantum states. Time might not be fundamental at all. It might be a way of organizing the history of changes in information. And space, that might just be a convenient map of which pieces of information are most entangled with which others. Let's return to quantum error correction. One of its key features is redundancy. You can lose part of the system, and the whole still functions. In the Add CFT-inspired picture, this redundancy shows up in how the bulk space-time can be reconstructed from different parts of the boundary theory. That is, there's more than one way to describe what's going on in the interior of the space from the lower dimensional data on the edges. That redundancy is what gives rise to the robustness of space-time geometry. It's like saying that the reality of space-time is encoded not in any single part of the system, but in the patterns of entanglement across the whole system. And this may explain why gravity is so different from the other forces. Gravity, in Einstein's theory, is geometry. It's the warping of space-time caused by energy and matter. If that geometry is itself emergent from entanglement, then gravity might be a derived phenomenon too. It could be a manifestation of how quantum information tries to protect itself, to stay consistent, to avoid errors. What's fascinating is that these ideas are not just philosophical. They're supported by rigorous mathematical models and a guiding research into quantum gravity and the foundations of physics. Sean Carroll argues that our task now is to move beyond abstract models like ADS-CFT and find out how this works in our universe, which doesn't appear to be an anti-de Sitter space, but something closer to a de Sitter geometry due to the presence of dark energy. Still, the principle remains. If we can find the right quantum error correction code, the one that encodes our universe, then we might understand how space and time arise from quantum mechanics. And not just any quantum mechanics, but a version enriched by the concept of quantum entanglement and the need to protect information from loss. In a way, this idea unites several major themes in physics: the centrality of quantum information, the power of entanglement, the mystery of gravity, and the emergence of space-time. It suggests that the universe is not a machine, but a computation, not a stage, but a process, not an object, but a story told in the language of quantum codes. And that brings us to an even deeper question. If space and time are emergent, then what is fundamental? What lies beneath them? Carroll believes the answer might be found in what he calls the Hilbert space of the universe, the complete space of all possible quantum states. In this view, our familiar world, with its galaxies and planets and people, is just one tiny corner of that vast mathematical structure. One region of high redundancy, where error correction makes space and time look smooth and continuous. Other parts of that Hilbert space might look very different. They might not have anything like space or time at all. They might be unrecognizable to us, but they are no less real. And if we can learn to read the patterns in the entanglement, we might be able to glimpse those other regions, or at least understand what makes our own corner feel so familiar. This is not science fiction. It's not mysticism. It's rigorous frontier physics. It's an attempt to use the tools of quantum information theory to answer some of the oldest and deepest questions humans have ever asked. What is space? What is time? What is reality made of? And how does it all hold together? So the next time you look up at the stars or watch the hands of a clock move, remember, what you see might not be what's fundamentally real. The stars might be patterns in a giant quantum computation. The ticking of the clock might be just an emergent rhythm of entanglement. And the universe itself, it might be an error-corrected story, written in the language of quantum codes, unfolding not in space and time, but giving birth to them.